My great pleasure to introduce Gabe Hoshino. So he was actually here with us when he was an undergrad student, but since then he went over to University of Chicago, and there he's been working at Formula of Chicago, Argonne, and all sorts of things. And today he'll be telling us about his work on Axion search with bread.
Yeah, thank you. Yes, I'm Gabe Hoshino. I'm a fifth-year grad student at the University of Chicago. And yeah, it's really good to be visiting here again. So I'm going to start by sort of introducing the concepts of like axions, dark matter, strong CP problems. So all of the sort of background we need to get started here. So first of all, why do we care about axions? So the main reason we care about them is that there's a proposed new particle that can solve two long-standing mysteries in modern physics. The first is basically a question like, what is dark matter? What is it made out of? And the second is called the strong CP problem. And I'm going to go through both of these in a little more detail next. So starting with dark matter, the sort of initial evidence for dark matter is in sort of the first half of the 20th century. This astronomer named Fritz Zwicky was looking at galaxies in the Kalma cluster. And basically what he found is that they seem to be rotating so fast that they should like fall apart. There's not enough matter in them to hold them together gravitationally. So this is called like a flat galactic rotation curve, which you can see there. So you would expect that the velocity would like sort of fall off like that, but instead it stays flat and high. So Zwicky basically thought, oh, maybe there's a lot of matter we can't see that's not interacting with light. And he coined the term dunkel Materie, which is like basically dark matter in English. And now if we go to sort of the more modern age where we have much more like precision measurements in cosmology, we have the CMB. So this is the cosmic microwave background. This is basically the earliest light that we can observe from about 300,000 years after the Big Bang. And you can see sort of a heat map of like the temperature variations. It's very, very, very uniform in temperature. So these are very small temperature variations. And then if you do sort of a Fourier transform of these temperature variations, you get the actual details of this don't really matter too much. But my point is that these dots are sort of measurements, and this green line is a model, a cosmological model in which more than 85% of the matter content of the universe is dark matter. So in this precision age of cosmology, we know that not only does dark matter probably exist, it also probably makes up most of the matter in the universe. Okay, so what's the sort of, we know, I kind of told you what we know about dark matter to some degree. There's also a lot more evidence that I'm not talking about now. So we can sort of see dark matter on a macroscopic level. We can also like almost literally see blobs of it like bending light in our telescope data, which is kind of cool. So we kind of have a macroscopic understanding of dark matter to some degree. But the puzzle is that we don't really know what sort of what dark matter looks like on a quantum level, like what it's made out of, how does it interact with fundamental particles. So just as like a little example, it's not really related to any of the rest of my talk. You can just see a bunch of Feynman diagrams showing like interactions between axions and particles in the sun to produce solar axions. But this is just an example. It's actually not related to my talk. Okay, and then moving on to so that's one of the sort of big unsolved problems in modern physics. Another big problem is the strong CP problem. And basically it can be stated that like the theory of the strong force naturally contains some level of CP violation, which I'll talk about in a second. But no experiment has really measured any like CP violation of the strong force. So we expect it to exist, but it hasn't been measured. So that's sort of the puzzle. So first I'll sort of go into what CP means. So this is like different types of symmetry. So basically C-symmetry is if you take a physical process and swap out all of the particles for antiparticles. If that process basically looks the same, we say that it's C-symmetric. P-symmetry is if you take a physical process and reflect it over a mirror. If that process looks the same, we say it's p-symmetric. And then CP symmetry is just a combination of these two. So if you can swap out all the particles for antiparticles and reflect over a mirror, and you can't tell the difference between that and the original picture, that's what CP symmetry is. And then there's a final symmetry, which is called time reversal symmetry. And it's kind of what it sounds like. So if you sort of watch a physical process as if it was a video and play it backwards, if it looks the same, then you say it's T-symmetric. And it turns out that for like fancy quantum field theory reasons, any sort of consistent theory of particle physics we could make should obey CP and T simultaneously. So CP and T, if you apply all these transformations, it should be conserved. And that's called the CPT theorem. Now, on the right here, you'll see this is electric dipole moment. To sort of foreshadow things, we could say it's a neutron electric dipole moment. And you can see that if we apply a parity transformation to it, it flips the dipole, but leaves the spin untouched. So we started with something where the electric dipole moment and the spin were pointing in the same direction. Now they're pointing in opposite directions. Similarly, if you apply a time transformation, you can flip the spin, but you actually leave the dipole untouched. And since we can see that P and T symmetry are violated, and that also means by the CPT theorem that CP symmetry is also violated. And you can derive all sorts of other things, like for example, C should be conserved and a few other stuff like that. And again, if we pretend that this is a neutron electric dipole moment, that sort of gets us closer to where I'm going with our next discussion. Okay, so now let's talk about the source of this CP violation in the strong force. So it basically comes from this term in the QCD Lagrangian, which basically tells us the interactions that can happen in the strong force. This term comes from really scary topological stuff that I don't know how to explain, but I can at least tell you that that's where it comes from. And then at low energies, where quarks sort of get a mass from electroweak physics, this sort of receives a correction. So the real parameter that sort of measures how much CP violation in the strong force is this theta bar, which is a sum of this sort of topological term and this electroweak term. And that'll be important in a second. So, okay, so what's the actual CP problem? So the strong CP problem is basically that, you know, we have this theta bar, which we can allow generically to be non-zero. But if we go out and try to measure CP violation in the strong force by looking for a neutron electric dipole moment, we actually have already constrained theta bar to be like less than 10 to the minus 11 or 3 times 10 to the minus 11. So theta bar is really small, or maybe even consistent with 0 from our measurements. And this is a bit disturbing because theta bar and theta electroweak are generated by extremely different physics. Like this is from the topological vacuum of QCD. This is from electroweak physics. And yet they just cancel out to be almost exactly 0. So that should make you feel a little bit uncomfortable. To sort of highlight this a bit more, this is an analogy that my advisor really likes, David Miller. So this is an analogy from Pierre Sikivi and Science and Physics Today. And basically, you could imagine that if you're like a pool table maker and you have clients who have slanted floors, you could very, very carefully sort of make legs for these pool tables such that you perfectly cancel out the slant and you have a perfectly level surface to play pool on. And this would be very similar to sort of like theta naught and theta electroweak canceling each other out. And maybe for a pool table, you're not so disturbed, but pool tables are artificial, whereas we sort of expect these sort of natural parameters to be more natural than this. So it's a pretty weak analogy so far, but I think it gets more powerful once we look at it this way. So basically, the Axion solution to the strong CP problem is to propose a new degree of freedom in the standard model, so a new field called the Axion field. And it basically allows theta bar to dynamically relax to 0. So going back to this pool table analogy, it's like if instead of carefully making these legs the perfect length to cancel out the slant of the floor, you put your pool table on an axle with a weight and just let the weight interact with the gravitational potential to minimize the gravitational potential and just automatically level your pool table. So very similar to this, the axion introduces a degree of freedom, which is the axion field, and the axion also has a potential, and the axion will minimize its potential, and when it minimizes its potential, just like this pool table leveling mechanism, it naturally sets theta bar to 0. And then finally, we can even think about axion particles with this analogy. So maybe when you were setting up this pool table leveling mechanism, you had it at a small angle off of its minimum, and it started to rock a little bit after you release it to get to its minimum. And the axion particles are basically this little rocking around the minimum of this potential. And it turns out that these particles are massive and in some models have feeble coupling to other particles. So that also makes them a really good dark matter candidate because they have mass, so they interact gravitationally, and they don't have many other interactions with standard model particles. Okay, and then finally, like, how do we look for these things? So a lot of experiments out there use this coupling. So this is an interaction between axions in which and a magnetic field, in which axions convert to photons. And the photons basically have a frequency that corresponds to the axion mass. But the problem is, so that this photon produced with a frequency that depends on this axion mass, but we have no clue what the axion mass is. You can see that this is like more than 15 orders of magnitude. So this is the photon coupling strength. So basically the strength of the coupling strength of this interaction there. And yeah, you can see that very little of it has been excluded, and there's many orders of magnitude. And we go like all the way from like a regime where we can treat dark matter as sort of like this nice coherent wave, and we get like sort of microwave signals, up into like infrared where things are like more optical, and we have like photon counting because the rate of particle interactions in our detector goes down to like single particle levels. So anyway, my point is that we need a large group of many different types of experiments to cover this range, just because there's so much physics in all these different regimes that need to be adjusted. Okay, and so that's sort of the background. Now I'll sort of go into talking about BREAD, our most recent science run, and then after that I'll move on to talk about like our current focuses and how we can improve upon it. Okay, so talking about BREAD first. So the way that BREAD works is, again, we're looking for axions through this coupling. So we're basically looking for photons that are produced by axions that convert to photons in a magnetic field. Another way we can sort of think about this that's useful for understanding BREAD is that in the presence of an external magnetic field, we can get an axion that produces an oscillating electric field that's parallel to that magnetic field. So basically, as axions go through this detector, they're making an electric field that points up and down, that oscillates up and down inside of the detector, and then at the reflective walls of the cylinder of this reflector, they're conductive, and if you remember from E&M, the parallel component of electric fields have to vanish at the surface of conductors. So in order to maintain that boundary condition, the wall basically has to radiate photons as an axion passes through. So okay, so basically, yeah, we got axions passing through, we got the radiation of photons at the walls of the reflector, and then finally this geometry is basically like a weird parabolic reflector. So it focuses the signal photons to some focal spot where we can then place an antenna or some sort of sensor to look for a signal. And then comparing this to something a bit more standard and established in this field, we have resonant cavities. So resonant cavities, instead of instead of having like axions drive photon emission at the surface of a conductor, the axion can induce this oscillating electric field that drives a resonant cavity with some high quality factor that resonantly enhances the axion photon conversion. And then the main sort of takeaway with this is that these resonant cavities have to be at the scale of half a wavelength of the signal that you're looking for. So, so they're sort of, since you have to sort of satisfy this resonant condition that your signal fits, half the wavelength of your signal fits in this cavity, they have a sort of very limited range of frequencies that you can see at once. And resonant, I think this is a picture of actually a haystack cavity, but resonant cavities have a tuning rod inside so that you can sort of change the internal geometry to sort of change this half wavelength scale so that you can then scan across a frequency range. Okay, so then sort of comparing these resonant cavities, they have a signal power that scales with the quality factor of the cavity, the magnetic field squared, and the whole volume of the cavity, because the axion can sort of drive the resonant mode in the entire volume of the cavity. They are narrow band. They have a resonance enhancement, so you can see like this Q basically multiplies their signal power, and if you have Q like I think you can get Qs like 10 to the 4 to 10 to the 6. This can be like a pretty good like several order of magnitude improvement to your signal power. But then the problem is that since this volume is related to half the wavelength of your signal, this volume can become extremely small as we go to really high or really short wavelengths. For reflectors, the signal power scales like B squared A, so it depends on the area, not the volume of the reflector. It's broadband, there's no resonance condition, so this focusing just kind of happens at almost any frequency up to like limitations of your sensor, more or less. Yeah, so the main advantage is that we can keep this area large even as we go to extremely short wavelengths. So we lose this resonance enhancement, but we can keep the area large is basically the trade-off. And just to sort of underline the broadband nature of this concept, on the left you can see sort of a ray tracing simulation of the reflector just like focusing rays, and on the right you can see even like in the microwave regime, we get that the waves all get focused to a focal spot, and this is even showing a little antenna measuring that power, which I'll talk about in a second. Okay, so maybe you've looked at the bread reflector and you've wondered why it's a crazy shape instead of something a little bit more standard. I mean, like, it's a very weird shape for a parabolic reflector, but the main reason for this is that it's optimized to fit inside of large, readily available solenoid magnets. So yeah, it's basically optimized with a cylindrical symmetry and such that the B field of a solenoid magnet can be parallel to the walls of this cylinder as much as possible. And yeah, it's not even just a cartoon anymore. So recently we were able to put a bread reflector inside of a magnet at argon and take some data with it, which I'm about to talk about. And yeah, so and finally, so like in our concept paper, we sort of have this plot which shows how, since the reflector is a broadband is a broadband apparatus, the sort of hope is that eventually we could just have like a big, really nice flagship reflector and swap out the sensor or antenna at the focal spot to cover a large frequency range, because the sensitivity of any given run is basically limited by the sensor or whatever we put at the focal spot to look for this to look for the signal. So here you can see how we can cover a pretty large frequency range by basically swapping out different quantum sensors. Okay, and moving on to our actual science run. So Gigabread is our sort of pilot experiment, and the first actual science data we've collected with a setup like this. We started at this sort of low frequency of like 10.7 to 12.5 gigahertz, which is low for bread because we're aiming to go, even up into the optical regime. Yeah, in this sort of regime, we can couple this reflector to just a microwave antenna, and it's basically the sort of coaxial horn antenna shown here, which I'll also talk about more in a bit. So you can sort of see why we would start with an experiment at this lower frequency, and that's because you might look at this. This is what the reflector we used. You might look at it and say, oh, I can see like machining marks and all sorts of like surface imperfections. But since we're working with centimeter wavelength photons, this is actually basically a mirror finish. And this is a lot cheaper mirror finish than we could to get than if we were to try to get something that's like actually optically polished to some that we could use for like an infrared experiment, for example. So just a much lower barrier to entry. Yeah, and here is what our coaxial horn antenna looks like a bit more up close. It's a coaxial antenna, so there's an outer and inner conductor, and there's also this like disc of dielectric that's screwed onto the front to sort of hold the inner conductor in place. So that's just really there for structural support. And okay, so we designed these antennas and optimized them in simulation with COMSOL, and then we basically need to make sure that the antennas were behaving as expected. So one way to characterize antennas is with a far field measurement. So it's basically like a measurement of how much, what fraction of power an antenna radiates in different directions around it. So you can see here, this is a standard pyramidal antenna, and you see it radiates as you would want, most of the radiation directly in front of it. Our antennas are a bit weird, as I'll explain in a second. Our antennas, instead of radiating, so the antenna in this case is like just pointing down. If you look at these these radiation patterns. So our antenna doesn't have a big lobe just at 0 degrees like you would expect with more standard antennas. It actually sort of looks to the sides. And this sort of makes sense if you think about it, because with bread, most of our radiation is coming in from an angle. It's not coming from straight down, because straight down is this like parabolic focusing cone. So this is actually perfect for us, and we designed the antenna to have a pattern like this. So you can see a comparison between simulated and measured, and also the far field pattern at different frequencies. And you can also see our setup here. So we basically had 2 antennas on robotic arms, and I could point them at each other and rotate them to different angles with respect to each other, and sort of measure the transmission between them. And you can see me in an anechoic chamber doing this measurement. Okay, so after we sort of had an antenna that we convinced ourselves works, we needed a way to make sure that the antenna was at the focal spot inside of the reflector. So in the final experiment, we sort of had the antenna mounted inside of this of the cylinder of the reflector, and it's on a motorized little mount. So the antenna can be moved up and down inside of the reflector into and out of the focal spot. So basically, we needed to make sure before we started taking data that the antenna was at the right height inside of the reflector to be on focus. So in simulation, so this is a simulation basically of how much power, so simulating a dark matter signal and then seeing how much of that simulated dark matter signal power arrives at the antenna at different antenna positions. So there's different heights inside of the reflector. You can sort of see, probably as expected, on focus, the amount of power we receive is maximized. And then similarly, sort of importantly, if we then, instead of measuring how much power we receive from a dark matter signal, we just like essentially measure the reflections the reflectivity of the whole setup. So basically we have the antenna radiate a signal into the reflector and then see what fraction of that power comes back. We can see that this reflection is also maximized on focus. So this is basically maximizing S11 if you're measuring it with a network analyzer. And you can see that this is, and in the lab, we also get something very similar. You can see there is Stefan Knirk, who's now faculty at Harvard, doing this measurement with our horn antenna on the little robotic mount. Okay, and then moving on to our amplifier chain. Another reason why it's nice to work in this frequency range is we can have our entire amplifier chain just with like off-the-shelf parts and still get pretty good performance. So it's mainly off-the-shelf parts. It's just like a low noise amplifier with some more standard amplifiers and some band passes, and then we sort of mix down our signal. It's a pretty standard receiver chain where we just like mix down our signal into a frequency range that we can read out with our data acquisition board, which is like 0 to 2 gigahertz. And this is what our data acquisition board looks like. It's a Xilinx CC111, and it has real-time FFTs and averaging implemented in the FPGA firmware, so it can do that pretty quickly. And it was developed using this like KIC toolkit, which was made at Fermilab. And yeah, it can basically do a 2 gigahertz bandwidth simultaneously with 4 gigasamples per second. Okay, and then just like to highlight one of our RFI mitigation schemes that sort of combines that with the receiver chain I just showed you. So basically, we were taking data actually in an anechoic chamber, but even in an anechoic chamber, we were seeing a decent amount of RFI, especially like in the readout band, so like in the 0 to 2 gigahertz that our DAC board was using. So one way that we were able to mitigate this is we just like had the local oscillator frequency hop around as we were taking data. And what this did is it would basically like, since the local oscillator hopping around essentially affects the high frequency signals different than the low frequency signals, it basically smears out these lower frequency RFI into their neighboring bins until they're no longer very significant. Okay, so combining all of the stuff I just showed you, we put everything in the basement of a building at the University of Chicago in this anechoic chamber and took data for 24 days. Throughout data taking, we moved this horn antenna up and down into and out of the focal spot. The reason why we did that is because, yeah, you can sort of see like these sorts of dips in the reflectivity, and that's because of weak resonances between the antenna and the walls of the reflector. So basically, to sort of smear out these weak resonances and get more even sensitivity across our frequency range, we move the antenna up and down during data taking with a cycle of about 4 hours. Okay, and we ended up not seeing anything, which means that we were able to set a limit. So here is a limit that we set on dark photons. I know I didn't really introduce dark photons, but they're basically they're very similar to axions, except they don't require a high magnetic field to convert into standard model photons. So they're sort of they're often like the first science experiment done with by like axion groups because you don't need an expensive magnet yet. But that being said, we did get our hands on a magnet. So there was a 4 Tesla magnet at Argonne National Laboratory. It was actually in the end only ramped to 3.9 Tesla. Yeah, we were able to have access to it for a bit. You can see sort of our team that summer. So we had a few summer students, Derek Rodriguez, Ben Knapper, and Mira Littman, who's about to graduate from U Chicago. We have me, and then we have Andrew Sonnenschein and Stefan Knirk. Andrew Sonnenschein's a scientist at Fermilab and Stefan's faculty at Harvard. So yeah, so one thing about argon compared to the dark photon run we did in the basement anechoic chamber at University of Chicago is that argon was a much louder environment. You can see that we're like kind of in this big open like warehousey space without any nice shielding around. Also, you can't really see it, but right out of the frame in these pictures to the left is the Argon Wakefield accelerator, which was on while we were taking data. So we were like actually trying to take data next to an active accelerator. So for that reason, we needed a lot of ways to mitigate this. And one of them is by putting a bunch of shielding in there. So we actually stole some of the foam from the anechoic chamber at the University of Chicago. And then I had some undergrads, Mira Lippman and Alex Lapuente, help me put this shielding all around the reflector inside of this magnet bore. And another thing we needed, because even with the shielding, some amount of background was getting through, we needed a background beta antenna, which I think I just saw Haystack has something similar. And yeah, basically it's a copy of our receiver chain, but it's just attached to a little pin antenna that pokes in through the shielding. And it's basically just like to veto any signal produced, or yeah, any signal that sort of bleeds in through the shielding. And it's outside of this reflector, so yeah, it's pretty unlikely that we would like mask any signals from an axion. Yeah, and yeah, so basically every so-and-so amount of time, you would sort of compare the data in these two and mask the frequency bins where you saw a background in the background veto in our signal data. And you can see it sort of removes these last like straggly peaks that we were getting. Okay, and yeah, this is, we also ended up not seeing any axion-like particles, and we were able to set this limit. It's the most sensitive laboratory experiment, or I guess like the only laboratory experiment in this frequency range. And you can also sort of see on this big plot like how broad it is relative. I mean, for only a month of data taking, it's pretty crazy broad. And this is also apparently like the first axion-like particle search using a dish antenna, which is also really exciting. Okay, so that was our most recent science run. Now I'll sort of talk about what is currently in development with bread, like how we're looking to improve this and move to higher frequencies and also be more sensitive. So the first improvement is at Harvard, they're receiving this sort of really nice dilution refrigerator that has a built-in 8 Tesla magnet. So they had a sort of smaller version of a bread reflector made that can fit inside of this magnet, because the one that we used for our data taking at Argonne is much too big. Yeah, they're basically hoping to do a very similar experiment, but now cryogenically. First, maybe with off-the-shelf amplifiers, and then eventually something that's more like near quantum limited with a Ki tupa from NIST. And yeah, so you might wonder, like, with the smaller reflector area, how does this perform relative to our room temperature experiment with a much larger reflector? But so it turns out that this higher magnetic field strength and going to cryogenic temperatures, so making your noise performance better, actually does give you pretty compelling sensitivity over our pilot experiment, as you can see. So this is the dark photon projected sensitivity and the axion-like particle projected sensitivity. Okay, and so another direction that we're taking bread in is we're calling it quality bread. The basic, it's basically because it's a funny name, and it's basically because we're now making bread slightly resonant. So there's a little bit of a resonance enhancement now. You can see here we're getting about 2 orders of magnitude with our current design. And yeah, so the basic idea is to, instead of having an antenna at the focal spot, we replace it with a secondary mirror to make something that's like almost a Fabry-Perot cavity. And then we get this comb of resonances that we can tune by like moving the secondary mirror up and down. And you can also see that this is also pushing to higher frequencies. So this is at nearly 100 gigahertz, so more like millimeter waves. So in simulation, you can see that this tunes pretty well. So moving this reflector up and down, you sort of move these peaks in the frequency space. And you might wonder, like, isn't this sort of a huge trade-off? Isn't this sort of like a huge departure from our usual broadband goals? And it kind of is, but it's still not a resonant cavity. So we're not moving one peak across this entire frequency range. We have many peaks, a comb of peaks, and we actually only need to scan the distance between 2 peaks effectively. So so in the end, we do actually, and also we do, it turns out that you do get an improvement in scan speed from these resonant enhancements over like a fully non-resonant case at least. And here's like what the sensitivity projections would look like for something like quality bread. So yeah, so I should say, so finesse is basically like it's very similar to quality factor. It's subtly different, but the point is that it's basically a multiplicative factor on your signal power in the same way that quality factor is. And yeah, so we're currently getting a finesse of about 100 with our current design. So basically, if we improve by a factor of 10, go quantum limited, and get a bigger dish antenna, we can like maybe get beyond the astrophysical bounds. For axion-like particles, for dark photons, though, it's a pretty open parameter space. Okay, and then going to really high frequencies, our collaborators at Fermilab are building infrared. So infrared is, as the name suggests, it's like an infrared experiment. So at Fermilab, they have these SNSPDs with a 1 millimeter squared active area, and they're also trying to make them with a lower threshold. So I think they currently have them working in the far infrared or in the near infrared, and they're trying to get them to lower frequencies in the far infrared. So we have these sort of SNSPDs that are being characterized for use with a bread-like experiment. We also have this beautiful optical grade reflector, which was diamond turned at Lawrence Livermore National Lab that you can see here. It's really shiny and polished, unlike the gigabread reflector I showed earlier. And yeah, efforts are sort of underway to characterize the beam of this a bit better so we can understand how to calibrate it, like calibrate the position of an SNSPD inside of something like this. We're hoping to eventually have like maybe something even like in situ because it's a little bit difficult to figure out like in situ how to place this, how to move this SNSPD like exactly into the focus of this reflector while you're taking data. Okay, and then the sensitivity of this is basically the plot I showed earlier. Yeah, so that would be sort of this upper range showing like what parameter space we could maybe tackle with something like this. Okay, and then the last sort of direction for like improving bread that we're actively working on now is dielectric enhancement. So maybe you guys have heard of Mad Max, but basically if you have a bunch of dielectric layers and your magnetic field pointing this way, at every sort of interface where like between like dielectric layers, where there's like an abrupt change in dielectric constant, you can get the emission of axions or the emission of axion converted photons. And then you can also get standing waves between and inside of the dielectric layers. So you get like a resonance enhancement. So basically you get a increase in like the effective area of your experiment and also like a small resonance enhancement. So these two combine to give you like an overall thing that the Mad Max people call the boost factor, which is another sort of multiplicative thing that multiplies your signal power. And the idea is that maybe we could put dielectric stack sort of along the walls of a reflector like bread to essentially increase the effective area and just like get this boost factor to multiply our signal. Okay, and then again, you might be wondering like how broadband is this, because there are these sort of resonant effects that depend on standing wave. Like you need, first of all, like all the photons to sort of add coherently, and you need the standing waves, or the standing waves between and within the dielectrics are basically resonances. But it turns out that you can make something called a chirp stack, where you very gradually vary the widths of your dielectric layers from layer to layer as you move through the stack. I think you can also gradually vary the dielectric constants as well. And if you do this, you can actually get a stack that has a boost factor supposedly of so a boost factor supposedly of like order 100 and with like a 30% bandwidth. So that's sort of this like orange line here is basically showing a 200 layer chirp stack where like the calculations were done sort of in theory. Yeah, so I should say like all of this is like theory for now. Like no one has actually built a stack that actually does this yet. So the people at Harvard are building a setup to sort of begin testing and developing dielectric stacks like this. So what they have basically is they have this like rotating stage where they can put dielectric stacks. They have a set of antennas and mirrors that can like essentially shine a signal through the dielectric stack and look for like reflections and measure like the reflections and transmissions. And then they also even have like a cryostat with a window in it that they can use to do these tests cryogenically. But for now, they've mostly been doing room temperature testing. So you can see this is like the room temperature setup. They have a 5-layer stack consisting of silicon disks with air gaps in between at room temperature. And yeah, this is being done by Harvard grad students Grant McIntyre and ICJD. And yeah, so they did the measurement, and it turns out that it agrees pretty well with analytic models for like the reflection and transmission measurement. You can see that there's like still these artifacts on here. This is extremely like fresh data that I like asked them to send to me right before this talk, so that's why it hasn't been removed yet. But presumably you could get rid of this by doing like some sort of windowing in Fourier space. And yeah, so this is looking pretty great, and they're going to try to do the same measurement cryogenically coming up really soon. Okay, so now looking to the extremely distant future, how could you like hit the QCD band with something like bread? So you could do this in like several phases. The first one is something with like quality bread. Like sort of the best version of quality bread could get you to like that region shown there. If we move up to like TerraBread, we move up to something called TerraBread phase 2. This is and this is like tackling like again like millimeter wave to sort of like terahertz regime. So if we move up to something like with a bigger reflector, bigger magnet, and a boost factor that's already like something that we're like reasonably confident we can achieve with off-the-shelf amplifiers, we can improve our sensitivity a bit further. But then, like you can see, to get to the actual QCD band, we would need a much higher boost factor, quantum limited amplifiers, a bigger magnet than exists in the world right now. And yeah, so there's definitely a lot of work that has to be done, especially like you can see the dielectrics need to improve by an order of magnitude. But this magnet thing, I guess like my point bringing up the magnet thing is that these the sort of magnets we need for a lot of these flagship Axion experiments are like a hard burden for any one collaboration to carry. So Fermilab basically is trying to make this large scale magnet facility. And I chose 9.4 Tesla in that projection for a reason, because that's the strength of this magnet that was just delivered at Fermilab. But yeah, so the idea is basically maybe someday Fermilab could start this thing called the Dark Wave Lab, where they have this large magnet that we got from University of Illinois Chicago, and different groups can sort of like come in and run experiments in it, and like reserve time. So yeah, sort of like a shared magnet facility for several collaborations. So and I should say we also had like a workshop 2 years ago at this point, where we sort of discussed this idea with a bunch of different collaborations. Yeah, so here's a picture of this magnet getting delivered. And it's currently in a building where the old donut experiment used to be, which I find kind of funny, that maybe someday some like version of bread might be running in the donut building. But but anyway, but yeah, so someday maybe we'll get this magnet running and people can start using this, and hopefully this will get the ball running that maybe someday we can have this 20 Tesla magnet with a huge bore that we can actually fit an extremely flagship version of bread inside of with a really big area. Yeah, so thanks to the bread collaboration, we just had a collaboration meeting last month, so this is a picture from that meeting. And we have collaborators at quite a few institutions now. And also special thanks to Peter Winter and Simon Karodi from the Muon G-2 experiment. They basically helped with all of the logistics for like getting us in to take measurements in that 3.9 Tesla magnet at Argonne. And yeah, that's my talk. I can take questions. Yeah.
What happens to the power that doesn't make it to the antenna? Like, where does it get dumped? Is there an absorber behind the antenna?
Yeah, there's
the angles that don't make it.
Yeah, we have absorber. Yeah, we basically have absorber like all around the top like cap of the reflector. Yeah, for that reason, to sort of absorb all of these extra photons so that they don't form.
So your sensitivity to axion. So for us, we have like this form factor, I guess, which is like the integral of the field and the over the volume.
Yeah.
So instead, you need to take this beam and integrate how much of the beam hits your cylindrical walls, essentially.
So we basically also have a form factor, I guess, except it's really complicated. So as a sort of conservative estimate, what you basically can look at just the walls of the reflector. So we know for a fact that the walls are radiating photons perpendicularly, and those ones get focused. So that's sort of what we have instead of a form factor, I think.
But don't you have to integrate that with the frequency dependent beam pattern of your antenna?
Oh yes.
In the field of that antenna at the walls essentially needs to get integrated.
Yes. Okay. Yeah. So we do that in simulation. Okay. Yeah. So if that's what you mean, then yes.
How close is that to 1 overall frequency?
How close is that to 1?
How close can you just take the area of the wall of the cylinder? How close is that number to?
I think I actually have a plot of the. Let's see if I can find it. Oh, here. This is kind of, but yeah, you can see like this is essentially like how much of the power being generated like at the surface of the reflector is actually received. So this is an efficiency. This P naught is the power being generated. Well, okay, it's like if you assume fully non-resonant, you can see it actually goes above 1 here, and that's because of like resonant effects, because there are reflections between the antenna and the walls because it's not perfectly matched. But you can see this is roughly the efficiency of our antenna. And you can also see like the wiggles. So like this is why we had to move the antenna up and down during data taking, because we wanted to sort of smooth out the sensitivity. Yes.
Are photons also emitted from the parabolic surface or just from the cylinder? Why?
Yeah, they are also emitted from the parabolic surface. We're basically ignoring those and like letting them get absorbed by the absorber. But it's definitely less efficient than the cylinder, just because like the curve is not it's not parallel to the magnetic field, so it's like it's a little bit less efficient.
Yeah, a question about the sensitivity plots.
Okay,
It was
which
maybe 56 gigabyte.
this one or
The previous one, maybe 2-3 slides earlier.
this one or the one before?
Should
This one.
Yeah, why is there a gap in the frequencies for
Oh.
gigabyte pilot projections? I didn't quite understand.
Okay, so the main reason for the gap is just like a political one, which is that this is another dark photon experiment called BRASS.
Okay.
And like, I think the plan is that we ideally don't want to like rescan that for now.
I see. Okay.
So that's and I think that sort of propagates into our axion like particle prospects as
Sure,
well.
but in principle, you have sensitivity there. It's just
Yeah, in principle we could. I mean, this is also limited by our antenna. So for example, we currently don't even have an antenna that would work for this one. Our current antenna design only goes up until like 15-ish or something like that.
Okay, and then I think 2 slides earlier, 1 or 2 slides earlier, when you showed your dark photon results. This one, yeah.
Oh, the axionic particle,
Yeah. Why is there, as a function of alt mass, there seems to be a structure?
Yeah, so this is like not for any supernatural reason. It's mainly just like it's because of like the background vetoing mainly. So this probably says something about the Argon Wakefield accelerator more than it says about us. Because you can see like in our previous data run, there isn't anything nearly this crazy. Yes.
I guess I was just curious, so the photon emits perpendicular to the walls, the reflector, but then your magnetic field is along the wall. I guess when you like calculate your equivalent form factor, this is like the opposite of what we're like. It's like the electric field, it's supposed to be like parallel to the magnetic field.
Mhm.
But then in this case, isn't that the opposite, or am I?
Oh, well, I mean, the photon is emitted with a momentum that's like
Yeah.
perpendicular, but the electric field is,
Yeah, I guess it's still, yeah, I guess it's,
yeah, so it like fixes the photon polarization to some degree, yeah. But yeah, the photon is still like perpendicular, if that's what you mean.
yeah, but when you calculate the overlap between the E field and the B field.
Oh, I see what you mean.
Yeah.
Yeah, so we really only this is like, I think this is what I was trying to say earlier, which is like we really only understand that overlap at the walls of the reflector because of the boundary condition. There's some like mess in the middle,
Okay.
and maybe we're getting some extra photon conversion there, but since we don't understand that, we're being conservative basically and assuming that there's no extra signal photons being produced in the volume. but I think like maybe you could calculate this form factor and find that there is some small amount of photons being produced in the volume as well.
How do you do the calibration of this? You rely on the noise temperature and calculation, or is there a way you can inject a signal?
Oh, we did inject a signal, and we also used, well, we used the noise temperature as well to do like a gain calibration, as if that's what you mean.
It's hard to inject a noise signal that looks anything like the Axion.
Yeah, we injected a signal using a little pin antenna like in the side. And we were actually able to pick that up with our antenna at least. Yeah, we actually like blind injected a signal, so for both runs. So one of our undergrads like picked frequencies to put in. Let's see if I can get this. But one of our undergrads like picked frequencies to put in and didn't tell anyone who was doing the analysis like what they were, and then we found it. So yeah, this is like the dark photon blind injected signals. And this is like for the Axion like particle experiment. Yes.
For Haystack, there's like a certain, I always forget the short term for this, but there's a certain like ratio of diameter to height of the cavity that is practical. And so I was wondering with your parabolic reflector, when you're just thinking about ignoring the size constraints that you get from a like magnet, when you're thinking about trying to maximize the area, is there a certain diameter or length at which this parabolic reflector becomes unwieldy? Like maybe I'd imagine if the photons have to bounce too long to get to the antenna, there might be some signal attenuation or something like that. So is there like a sweet spot of diameter to height or something that you guys like to be in?
I mean, we just want to be as big as possible because it's like there's only, no matter what, it's two bounces, right? So it's emitted from the wall, it bounces off of the cone, and then it bounces off of the wall directly into the antenna. So yeah, and like the losses from like if we could get it in vacuum, but even in air, the losses are not so big. So yeah, so I guess we just want it to be as big as possible.
Oh, okay, gotcha.
And the height to diameter is kind of fixed by the geometry, because the focusing, there's sort of like a very like precise parametric formula that this follows.
Gotcha. Okay, thanks.
Who was first? I don't know. Okay.
I was just wondering, for a gigabit grad, you need to have a parabolic mirror on the top and move it up and down to tune the frequency. And is the gap going to limit the finesse that you can get out?
You mean for quality bread? Sorry. Yeah. Yes. So you're asking if the gap limits the
finesse that you can get?
It's pretty uniform, at least across our, I mean, at some point it just like, yeah, at some point we hit some limit where it stops working very well. But at least across our frequency range, it's like pretty uniform. Here, wait, let me like.
But is the sphere moving, or is it just the antenna that's moving? The sphere is just reflecting everything back into the cavity?
Oh, no, the sphere is moving.
The sphere is moving.
And then we have some sort of like probe that we stick in that we can hopefully maybe critically couple to, or like trying to work on that. Or maybe we have an aperture like more standard for like a Fabry probe cavity that we couple some amount of power out of through some like evanescent coupling. But yeah, you can see like the finesse is like pretty, like at least across like this frequency range is like pretty even. Yeah. Or but you haven't asked a question.
You had shown this like signal power proportional to QB squared volume or B squared area.
Yeah.
What's the length scale? That like, is there a physically important length scale difference between those two things? Right, like, or I guess I'm trying to get at like, is there an additional like fundamental difference in the signal power from a volumetric versus an area kind of source?
Or is there a length scale?
Yeah, like the units of B squared V are not the same.
Oh, I mean, yeah, I mean, there's a lot more factors in here, yeah.
So like it's not just like a unity factor, but it has some dimension. So like, do you know what that dimension is? that is setting how comparable these two signal powers are?
Yeah, I mean, I think
It's just a messy thing, maybe.
I mean, I think for one thing, this is resonant, so like this signal power will like to some degree depend on your wavelength.
I guess they could, both of them could be resonant though, I guess.
Yeah, so yeah, this one could also be resonant. But yeah, I guess here I'm like assuming that there's some sort of like perfect absorber at the top, but yeah, I guess in principle there should be some length scale. I would imagine it like is like half the wavelength of their signal, but I don't know. Or
So
this
does that tell you that one of them is more favorable at a certain axion mass, like fundamentally, or
Yeah, so my advisor was like just asking me about this like earlier when I was giving the practice talk. So I was like trying to calculate this at the airport yesterday, but what that fundamental like essentially when A is equal to QV or something like that, some sort of like comparison, you mean?
yeah, exactly. Like when is A equal to QV, and then what's the dimensionful factor that goes between those things that would tell you like
Yeah,
when to favor one or the other?
Yeah, so this is definitely something that I've been like, at least in the past 24 hours, been thinking about actually. So that's funny that you ask it. So I'm not exactly sure where that threshold is. I imagine there's also like it's also up to like it's also an extremely fuzzy boundary up to some like engineering cleverness. But yeah, I think definitely like once we're getting to like millimeter scale wavelengths, resonant cavities becoming pretty darn difficult to make.
Thanks, yeah.
So yeah, I was sort of going for like there is an extreme where we can say like this is crazy, but like I don't know where like the threshold is.
You've answered my question. Yeah, it's just related to the length scale of the axion, which is
Yeah.
I wouldn't have known. Yeah, thank you.
Yeah, I mean, I think underlying, if I understand correctly, underlying this is like, you're really just taking an integral of the field over the magnetic field, over the you know, the axion field. And in the case of a resonant cavity, you have a mode that's contained that has some 3D shape. And so then that integral pops out a factor of like volume and quality factor of the mode. But in the reflector case, it's just, you're assuming that you're only considering fields at the boundary.
Mhm.
And so you're now just integrating essentially along a infinitely narrow sheet along it could be a flat plane, or in this case, the edge of the cylinder.
Yeah.
And that tells you like which relevant part of the axion field gets
And so
is
It still has to have a volume length in order to.
Yeah, and this is like a simplistic picture because in reality we are like the photon in our reflector is coupling to a mode. It's just that we don't understand it because like in a cavity you're using the fundamental mode of your cavity, like usually like a really low order mode that's like relatively easy to understand. Whereas like we're using like an extremely high order mode of our cavity that we like don't actually understand very well.
then the axion length is setting like the dr like thickness of the like volume of what the volume integral would be, sort of maybe. Is that?
I think that has to be it for the microwave cavity. It scales like the wavelength cubed. For this, it scales like the wavelength. So that gives you the crossover point.
Okay. Yeah, thanks.
Sure.
I appreciate that. Yeah.
Jackie had a question.
I may have missed this detail, but like, were you always operating at cryogenic temperatures, or was it
No.
the quality bread that you guys stuck it in a cryostat? And like, what part of
So the experiment at Argonne and University of Chicago is all room temperature.
Okay, that's what I thought. So what part of the instrumentation performs better under cryogenic temperatures? I don't understand why we need a dosage.
Basically it's just that it's mainly like the receiver chain. So the receiver chain at room temperature we sort of get 300 Kelvin of like room temperature noise.
Okay.
And then additionally whatever noise, I mean when these amplifiers are hot they also like add thermal noise into our signal, right?
Okay.
So yeah, even just like taking, even just like moving from like, so this is our low noise amplifier, even just moving from a room temperature low noise amplifier to like almost the same thing, but cooling it down to 4 Kelvin or whatever, that can improve our sensitivity kind of a lot. Here, wait, let me like actually go to the, there. So yeah, so here you can see like, you know, this is essentially taking like this, almost this, a very like analogous amplifier to what we used at room temperature, which is called a Hempt amplifier, and we cool it down to 8 Kelvin, and we already get pretty decent performance. Yeah, and then the other reason why you go cryogenic is it even lets you use things that aren't Hempt amplifiers. You can move up to like superconducting, like almost quantum limited amplifiers, which are a little bit fancier. So that's really what you gain by going to cryogenic temperatures.
Perfect, thank you.